design. And we are very honored to have Dr. Carnasciali with us today, and so please join me in welcoming.
Thank you. Well, thank you for coming and despite of the weather. Okay. Just to give you a little bit of a sense of how I ended up doing this sort of work, I do fluids and thermal fluids design analysis. And last year I was at a conference in Baltimore, and every session I went to had something tied to wind. And I said, oh, I have to get into this. So here at UNH, I'd been doing a bit of analysis with parachutes and deceleration devices with local companies. And I saw this as an opportunity to use what we've been doing here and spread it out so I could do work with more students. Okay? The work that I've been doing with the companies has been very tied to U.S. citizens and government money. And this really opened up my eyes to try it to the college has an energy initiative moving forward, and I saw that as a good opportunity. Okay, so this past summer, I had an undergrad student work with me on a surf project, and we began trying to understand, an overview of where wind energy is right now, and how what can we do to contribute. Okay, and there we go. So just an overview of what we're going to talk today. I'll tell you a little bit what wind energy is. I know we have a broad audience. I'm not going to go too much into detail as to the current state of wind energy. Dr. Daniels did a talk 2 weeks ago. You might have attended that, and that dealt more specifically with that. But this will put it into context, and then really talk about what research questions are being explored related to wind energy, tying it at the end with the stuff we want to do here. So wind energy. Okay, so this is the idea that we take the energy that's inherent in the wind, kinetic energy that's in the wind as it moves through, and we're going to move propellers, and we're going to thus generate electricity. Okay, so we're going to get the energy from the moving air and use it to power our stuff. Here you see two pictures. This is a wind farm in Copenhagen. This was about 2003, so it's a bit one of the smaller ones with only 48 wind turbines. And so what we see here is that you can use one wind turbine, as you might have seen if you've crossed over the Q Bridge. There's one there with a paper mill company that has it installed there. Or you can use them in aggregate to get more energy out of them. This is one of the ones down in Texas. The United States has many of them. We'll talk about that in just a second. So how is it that it works? Okay, so here we have a typical horizontal axis. So if I move over here, the horizontal axis of the turbine. Okay, and wind is coming onto them and flows over the blades. So this is what we call the wind turbine blade, and that's going to create a torque and spin around my gearboxes, and that is going to be connected to a generator. Okay, so that's a motor. It's going to be turning, and in turning, I'm going to generate electricity. Okay. A little bit more about the fluids behind it. So this works the same way as your airplanes fly. Okay, with the idea of lift. So the air moves across the blades, and because of the shape of the blades, it's going to move at different velocities, creating different pressures, and it's going to result in a force that's going to make the blade turn. Okay? So it's the same thing as how your airplane creates lift flying. In this case, because it's attached to the center, it's going to rotate. So really, it's a matter of size. So if you've gone around and you've seen some of these installed from the car, they look rather small, but as you drive closer and closer to them, they look like ginormous apparatuses. How many of you have been able to be at the base of one of these? No? So I lived in France for a year, and you see them in the border of France and Germany, and you could drive through these wineries and try to get close to them, and you stand at the bottom of one and you just look up, and it's this ginormous building per se. Okay, so most of them have been 60 to 100 meters high. So think about on the 30th floor of a building. Okay, so that would be 27 to about 33rd floor. The higher you go, you can see that as time progresses and research progresses, they get taller and taller, and we'll talk about that in just a minute. The diameter of the blades gets equally large. So they started around 40 to 60, and now some of these GE ones are pushing the 100-meter diameter. Same thing with the capacity. It's been going up and up. Currently, some of the ones that are being installed in the wind farms in China range all the way up to 300 megawatts. This one that I have here from GE produces about 1.5 megawatts each. So remember, it's about adding them, right? The more I add them, the more energy I'm going to be able to get out of them. Why do they keep getting bigger and taller? Okay, that goes to this fact that the power I can get out of it, think of it as energy. The energy I can get out of them is directly proportional to the area it sweeps. So the more area I can reach, the more power I can get. But here's the critical part. It's proportional to the velocity cubed. So if I were to be able to, the velocity of the wind, so if I am able to get to wind that's moving twice as fast, the power output is going to go 8 times as fast, or 8 times as large. Okay? So this is why companies and research, the whole goal is to try to make them go higher up and bigger. I have, we go out sailing here in the Sound, and the little sailboat has a much, much smaller one. This 500 kilowatt would be if you're trying to produce actual electricity. If you have something that's just going to power one or charge your cell phone or something while you're out sailing or things, they're much smaller. So what's in place currently? The currently installed turbines, 81% of them are accounted with the United States and Europe. Spain, England, Germany have invested largely on renewable energy, so they have these throughout their nations. I put these 3 numbers here, these 3, so that you could see how we're progressing. Okay? So in 2006, the world capacity installed, so these were wind turbines that were out there generating power, were 73 gigawatts. Okay? So a gigawatt is 10 to the 9. Okay? By 2009, that number had more than double. And here in 2010, we reached a little bit above 200 gigawatts of installed power in the world. For comparison, if we looked at the United States, in 2010, we had 40 gigawatts installed. Okay? And that accounted for about 3% of the electricity that was generated in 2010. So wind is a small chunk. In the Bush administration, we started the analysis or the investigation as to how much can we go towards being produced from wind. And the goal is that by 2030, we'll reach 20%. Okay? So we're still shooting for that. There's several states that are already doing that. Iowa, South Dakota have already installations where their energy supply is large from wind. Here this year, value is based off of September, the quarterly announcement that came out, and that's 51 gigawatts. This corresponds to 40,000 turbines. Those little items installed 40. There's currently about 8.4 gigawatts that are under construction, so they haven't yet gone. So by the end of 2012, we should have about 60 gigawatts installed in the United States. If you have any questions at any time, feel free. I want to make this informal.
Nuclear power plants about 2 gigawatts
Yeah,
is about equivalent to 100 gigawatts.
exactly.
I mean, nuclear power plants.
Right. So a little bit about numbers, right? I keep talking about these wind farms, and that if you take one of these wind turbines and you add them up, that's where we were getting the power. So this is the largest wind farm currently active, and it is in China. It has right now 5 gigawatts installed, and their plan is that by 2020 they will have 20 gigawatts. Unfortunately, I wasn't able to find the count of the turbines that they have installed. The sign here says, from the caption in the picture, that optical transmission lines are on the ground, so you have to be careful with digging. The largest in the United States is the Alta Wind Energy Center. If you read the newspaper frequently, you might have heard of these. Google had a large investment in making this happen, and so most of these wind turbines actually have a Google logo stuck on them. It went live in 2010, so 2 years ago. It has 1 gigawatt if you want to compare it to the previous one. So this is 5 gigawatts, and how we have 1 gigawatt. So we've gone down considerably. And this has 390 turbines installed in the mountains in this is Southern California. The largest offshore went live earlier this year in the UK. Okay. This is Walney Wind Farm. It has 367 megawatts, so this is 0.3 gigs. So if you're comparing, we went 5 gigs, 1 gig, 0.4, right? And this is 102 turbines. Now the UK has made a large investment into wind power. They hope that they will have 18 gigawatts of installed capacity by 2018, 2020. So I mentioned a few minutes ago that the goal is to get us by 2030 to be able to produce 20% of the power generation in the US. So what's it going to take to get us there? What are we doing to get us there? And like I mentioned, states like Iowa and South Dakota are already upwards of 20% of their production. States like Texas have a lot of wind farms, but they also produce so much energy in other methods that percentage-wise just doesn't add up yet. Okay. So in order for us to be able to install these plants and get us there, one of the first things that we need to know is, where is the wind? Can we can we characterize it? So this came out earlier this year. This is from the National Renewable Energy Laboratory. And you could see these darker areas, that's the areas of high wind, the more desirable ones. Areas in the more yellow or green are lower velocity. So remember that that power goes with velocity to the third, sorry. So we really want to get high velocity wind. Previous to this data coming out earlier this year, we were working with a map that had come out in 2007 that had data back from 1987. So now NOAA, the National Oceanographic and Atmospheric Association, has signed an agreement that they will use their satellites, and when they're going out and doing collecting data, that they will input the data so that we have more actualized and fresh data in order for us to be able to understand and be able to map these things out with current data. Okay, so that's part of the research that's happening now, is really trying to understand the wind. This data is taken at 80 meters high up. So I mentioned that right now typical turbines range in the range from 60 to about 100 meters. So you can see how if we want to go higher up, we'll need new data. I think the picture next to it shows you where currently in the United States, where the plants are. The little darker ones, if I remember correctly, The darker ones are the ones that are going to be installed and planned out, and then the white ones are the ones that are already currently running. Okay? So you could see that they really map out well to the areas in the previous map. Right? So this have this area here, this area here. If you look, California actually has several, and in the map they don't look all that great, but there's areas where things work out just right. Okay. Questions so far? Yeah?
Question, how does the cost of wind energy compare to that of fossil fuels and conventional sources of energy?
Okay.
Higher?
Number-wise, I don't know. I know magnitude-wise. Right now, renewable energy gets put in the United States, gets put in with the others, so you could get it. Nuclear tends to be the cheapest at the moment. Okay. The issue with wind power and why we need to do this sort of research is so we can bring the cost down. Right? Installation costs a lot. The materials and that are happening aren't lasting what they had planned. So the cost is getting high. Compared to something like natural gas, it's still considerably higher.
So are there, so what incentives are there for them to actually go out and build these power plants? Are there government subsidies or something like that?
Right, and that's what's happening in countries like Germany and England. There's a lot of government subsidies that are happening in place, right? And if you, I guess in this area, yesterday with the election, we didn't hear too much, but there were states like Iowa that had very particular interest in having the government make sure that they're going to support the sort of infrastructure for putting more of these plants and supporting the fact that we're going to have wind turbine farm off of New England, for instance. Okay. The other part of the research, along with where's the wind, is, well, what's the potential? So there's been several studies that have come out as to, well, we don't have, the wind can't give us enough. We shouldn't really be investing into all of these power plants if they're not going to make a difference. Okay. But we see that data that's being collected, so at 80 meters high, which was about 2 years ago where they were shooting for, gives you about 10,000 gigawatts, so 10 terawatts of capacity. And if you go a little bit higher up, so another 20 meters higher, you can get another 12,000 gigawatts of energy. Right? So it's, again, that push to going higher. Right? In the petroleum companies, they need to go deeper to get the oil that's harder to get because it gets more valuable. Here, the higher you go, the more you can get. So there's that incentive for these companies to develop higher, taller, bigger wind turbines. And if we look here at the data for 2010, this is offshore, so this is about 50 nautical miles off of our coasts. And you can see that the number in the United States is slightly lower. Okay? So the incentive here is really to go for land base. So when I started this presentation to plan out, when we scheduled it, this was the quote on NPR that week. So just 4 million turbines would be able to fuel half of the planet's energy needs. I thought, how appropriate, I have to keep that. So Mark Jacobson is a professor of civil and environmental engineering at Stanford University in California. And Christina Archer is a professor of ocean science and ocean engineering at the University of Delaware. And they took out the question of, can the winds that we have, can they really produce the amount of energy that we need and that we want? And what they found is that yes, that capacity is there, that potential is there. If you look about 80 to 100 meters high, you have 80 terawatts. And to put this in context, by 2030, the energy need for the world, including transportation, which is a huge chunk of our energy, so not just electricity, it's about 12 to 16 terawatts, depending on the research that you look at, depending on who you ask. Okay? So here they said, yep, 4 million turbines will be plenty. You're going to be using less than 1% of the surface of the Earth to get this amount of energy. So just to put things in perspective, there's 2 million cars registered in New York City, and there's about 11 million cars registered in the state of New York. So if you take the base of these wind turbines as the footprint of a car, clearly these 4 million turbines would fit in what the land print of the state of New York would be. So, and that would be enough to power everything. Now we couldn't really install them there because they would be interacting with each other, and that's part of the other stuff that's being researched, and we're going to get there. But I wanted to make sure you sort of got what 4 million turbines would be like. So along with that study was about, well, what about storage? Right? So a lot of the issues we hear with wind isn't there all the time. Right? It comes and goes. And a study that was done by a professor at UCLA in combination with Stanford was that they could map out, hour by hour, the demand of California power, and they were able to meet that need by using a lot of wind, a lot of solar, a little bit of geothermal, and the existing hydroelectric power in the state of California. And with doing this, by matching when the winds were blowing and when the sun was shining, they didn't need to maximize their storage. So they claim, storage is not our need. But really, storage is a huge problem when we come to wind energy. With wind, where we had the installations of the wind turbines, they tend to be far away from our cities. So they need to have good transmission lines. If you've had any problems with the power in the past week, you're well aware that our grid needs some infrastructure, stabilization there. And there's very cool research happening in this aspect. Just this past couple weeks ago, there was a story out of the BBC where they're trying to use, so when the wind is blowing and there isn't demand for electricity at that point, they want to use that energy to cool down the air to cryogenic temperatures, and then use that later on when it's needed. Okay? So the idea is that you liquefy the air, and then when you need it, because the wind isn't blowing, you're going to let that wind come to temperature. That's going to expand. It's going to turn a turbine like it would do in a power plant, a regular coal power plant. That's what's happening. You have a turbine that's turning in there from steam going through it. So that's there's research in all aspects. There's research in the capacitors, in the materials that are being taken place. And for those of you who are engineers in the chemical engineering areas, the mechanical engineering areas, there's a lot of potential for work there. Okay. You've seen your cell phones, and I keep hitting this thing. You've seen the cell phones. The whole goal is to get those batteries smaller, last longer, right? Okay, same thing here. We need to figure out how to get the energy when we need it. So the question arises is, if we're getting all this wind energy, or all this energy out of the wind, can we be affecting the wind patterns and the atmospheric patterns? Right? So models have been done, and of course we do this by running numerical models and things of that sort. And this was done by a professor at the Carnegie Institute in DC in combination with the Livermore National Lab. Okay. And they wanted to do exactly that. So if we're taking out 6 terawatts of energy out of the wind, are we slowing down the wind such that it's going to affect our normal patterns? And their study found that at very high numbers, yeah, it does make an impact. But at the numbers that we need for production, the numbers that we're doing right now, minimal effect. Okay. So that was earlier in September. So when I put out the abstract for this talk, I said, oh, we'll have to look into 20 years. What's happening in the last 20 years? But there's been so much being done that really you could concentrate in the past 5 just to share.
As the demand for energy gets higher,
Mhm.
the government goes ahead, puts some restrictions on how much energy the windmill can use.
Okay, so assuming that we got to such large numbers, I assume so. But there's so many other things that would go with the restrictions for the turbines. One of the things that GE has been working on is how to make the turbine blades generate less noise, right? Because if you want to install them near where there's more populations, the noise has been a complaint. So that's one of the sides. So there's a lot of other regulations that would be in place before it even gets to that point. Okay. Other questions? So one that usually pops up with this one of the environment is the one about birds, and I forgot to add it in there. But yes, a lot of birds die from hitting these wind turbines. There's been a few studies that show that because of the humming and the noise that they make, that they actually attract bats. But a study that came out showed that more birds die from hitting buildings in New York City and in places like that. The high skyscrapers with the glass attract the birds, and when they hit it, they die. From cats and other animals, that the numbers didn't really balance out. So the argument that the wind turbines are killing the birds is not necessarily.
Don't they kill like these rare pelicans and raptors more than they do?
More of the others, right. So if you look at all of them in general, they try to argue that it doesn't, but it also has to do with where these are being installed, right? So to his question as to restrictions, yeah, there's some places where if there's these type of animals that are going to be more attracted to them, then maybe that's not the appropriate place to approve the installation of them. Yeah. So is the sky the limit? So that study I mentioned earlier about for the 4 million turbines. 4 million turbines. Well, it also talked about how if we go all the way up to, say, 10 kilometers up, okay, so that's 6 miles up, then we have the availability or the potential to get another 300 terawatts of energy that are available. The wind is so much stronger, it's so much energy there, that if we are able to capture that, maybe we don't even need to be installing plants out here. So there's a lot of research into, the next generation of wind turbines. So this one is by Alteros Energies. It's a prototype. It was tested earlier this year. Okay, and it self-powered went up. It only went up 300 feet. It collected its energy and came back down. Okay. Now, if they're not tethered so that the energy is coming, we need to have that storage. Right, so they're all tied together. But you can envision how we have satellites up in orbit. We have, if we are able to send some of these up higher up, maybe we're able to generate energy that we can use for travel, space stations, things of that sort. Okay. There's a lot of things that happen here, right? You have to be able to use some energy to get it there. You can imagine some kites that are slightly lower in places where, how do I put this? The military in places in remote locations, you could definitely tether something up, collect energy, and get it back down, where you're not necessarily going to be interfering with flights, birds, animals of that sort. Okay. I was going to say something else. Other things that are being worked on is this idea of alternate configurations. So what I've discussed so far has been the horizontal layout. So this is some of the ones where the blades are vertically up. These are drag devices. So instead of operating with lift, these are operating by actually pushing on the blade and turning. And this is a lab that belongs to Caltech, also in California. They're doing a lot of energy-related things. And they're trying to figure out if you're rotating them counter each other. So how does the wind patterns interfere? How does one reduce the potential of the other? And this is a simulation. So this is a computer simulation which is tracking the wind patterns and trying to see where the velocities go. Just to give you a comparison of what 10 kilometers up are, when you're in an airplane and you go up 10,000 feet and then you can take out your computers and your iPod so you can listen to music, that's about 2 miles up. Okay. So you can see how if you're going to go up 10 kilometers, 6 miles, you're going above that, right? So if you wanted to send these other items up to get energy up there, it's going to be in the way of those things. Really, it's going to have to take some coordination. So not only are we trying to coordinate flights and takes-offs and bird migrations, we're also going to have to counter for maybe some of these in the future. So in Connecticut, this is Up to Wind in Tarleton, Connecticut. They're really in the business of doing things for the one. So no wind farms. So this is to be installed in your farmland in your country. Here's a tank. Maybe you're using it to collect water supply, and you're sort of multitasking. Okay, so here's one with 3. Most of the ones I've seen so far installed have only had 1. The blades are slightly different. So there's research into what is the optimal shape, how we can get the most out of it.
Is this used for pumping or for electricity?
They can use them for both, but they're being used for electric production. So this is meant for you to produce about 250 megawatt hours per year of electricity.
I think it could be mechanical and electrical.
Right. So that's right. The idea of using wind is not new, right? Back in the Middle Ages, we were using wind to grind grains and process flour and things like that. So now we're really using it for electricity. Yeah. So what can we do here at UNH? So I mentioned earlier I do what a CFD is computational fluid dynamics. So what we do is we take computer models, computer software, and we try to see what the flow past objects would be. And so far I've been using this to simulate flow past parachutes, flow past re-entry vehicles coming back into the Earth or landing in Mars. Okay? And we want to use the same software to try to optimize the blade design. So going into this discussion here of longer, bigger, slender. Okay? And also the idea of optimizing the layout of the wind turbine. So that is something that's happening right now. So there was a meeting earlier this year, and it was sponsored by the Department of Energy, and they wanted to know what are the stumbling blocks right now. So one of the things that they're finding with the turbines that are installed is they're not lasting the 20 years that they thought they would last. Okay? So there's a lot of vibrations that are taking place. The wind energy interactions are not what they expected. Okay? So what they came out and said as a goal is that they need to understand the complex flows, the multi-scale complex flow in a wind farm system, okay? And that understanding that will lead to innovation. That's where us engineers come in. Okay? And that innovation for cost reduction, so that goes to your question, right? How do we get them to be cheaper so that we can install them, so that they can drive, so that we can get to that 20%? No?
How long do they actually last? Like, do you have to replace the whole thing? Is it like,
Maintenance-wise. Okay, well, most of them haven't been up 20 years. But they're finding that some of them are not lasting 20 years. And there's actually a lot of maintenance that needs to take place. Okay? And that's very costly, right? You have to send a human all the way up 100 meters, right? You have to make sure we don't have wind gusts. That's not going to happen. So if the electricity company last week wasn't willing to send their trucks and their up in 40-mile-an-hour gusts, can't do that here either, right? So yeah, the maintenance of them has become definitely one of those issues. And there's a lot, Dr. Gorthala over in mechanical engineering, one of the things he wants to research, which ties well, is the materials. What can we make these blades out of so that they last structurally sound longer and lighter.
Do people worry about these blades like whipping around and they're just like falling off?
Right. So hopefully the engineers did a good job and that's not going to happen, right? Yeah, they're much higher up. Just taking aside from that, I was just in Puerto Rico during fall break, and you're driving through the mountains to this place where Monsanto, the seed maker, I don't know if you've heard of Monsanto, they make a lot of the seeds for all the produce you eat. Well, they've installed these huge blades on their fields. And we were talking to someone who works there. And the training that they're getting it's astonishing. So these workers in the field picking the seeds and the things like that are being told, don't stare at it, okay, because you're going to see this flashing effect, right? If you're in the shadow of it, don't stare. If the sun is coming and you're staring at the shadows, don't stare at the shadows because you're going to see this sort of strobing effect. And if you've ever had a Nintendo or things like that, it tells you warnings that if you have epilepsy or things like that, a strobe light could trigger that. So that's happening. They're being given earplugs to cover the ears, right? So yeah, I mean, if one of those were to come out because it kind of fell, the structural damage below would be pretty bad, and one would hope that these companies, at this stage in time, they're putting safety factors that are really not going to allow for that to happen. One would hope, right? So let me show you, see, here's flow past some turbines. So this is being done in a lab, okay? And you can see how the flow is coming and the wind turbine is turning, and the pattern behind gets big, right, disturbs. So if you were to place another wind turbine right behind it, it's not necessarily going to get the same quality of air that it got here, and so the energy production might be different. So this is some of the stuff that's been investigated. Vortex shedding, okay, so that's a technical term. So here, let me simplify that for you. Here's a cylinder, and I blow wind over it, and it's going to create these little swirl patterns behind it. If you're ever out in the wind on a cold winter day, you can hear the telephone lines humming, okay? And that's being created from the wind blowing over those lines and leading to that shedding. And if you've been on an airplane, the time between one airplane takeoff and the next has to do with how long it'll take for that sort of pattern to disappear through. So that also has to be factored in when we're trying to make these wind farms, and how close can we get them together? Because we want to maximize how many of them we put out there so we get more energy, right? So there's work being done on that. We want to understand how each blade design, how is the flow past each of them, and that's some of the work that I'm doing with the undergrad students. Okay. Some of the people are doing it experimentally. So this is inside a wind tunnel at Hopkins University down here in Baltimore, and they shine lasers. This little pattern back here, what it does is it disturbs the air, okay? And then they send them over, and they want to see how the quality of the air that the first one sees compares to the one behind it and the different arrangements. Okay? Now, it's important for them to do this experimentally, because then people like me who do a computer model, what we need to be able to link them. So it really needs to be tackled from both sides. So this is data from this experiment. And so these little black lines represent the wind turbine, and the color represents the velocity. So you could see how there's, behind the blades, the velocity drops drastically. And so you really need to place them sufficiently apart so that the next one is going to get the same quality. This is another simulation of the spacing between the turbines, and you can see here they have 3, and then they start putting 9, and so the air here is coming from this direction. If you put them in this organization, the one behind it isn't getting anything. It's not really going to produce anything. And then they have them in different formats. Part of what's being tested is if we take the blades, and I don't know if you've seen the flipper of a whale or a porpoise, they have all these little bumps. right? So what they're trying to do is they're trying to instigate that turbulence and break up that wind faster. Okay? So that's also being done to the blades, trying to change those shapes. How does that interfere? Will it make it go faster so that the next one can be placed closer? And now I can post the videos. Hold on, let me bring it back so I can see it on my screen. It started from the beginning. Questions while I pull that up? Okay, so here's an example of what I've been trying to do with a student this summer. So undergrad student. And the goal is that we want to change the shapes of the blades so that we can see and we can compare one blade to another. Here's Okay, this is one of those, this one's not mine, but this is one of those vertical axis turbines. And so in this case, the axis is standing up and you want to try to move them around and you want to understand the velocity patterns and the pressure patterns behind them. Okay, and the last one I have, okay. So this is, again, a computer simulation, and you have two turbines, one after the other, and in this one they did a little visual so you can see inside. The goal is that somebody needs to collect the data so that we know if the experiments are. And by doing this, we're empowering those who design to do that better. Okay, so that's most of what I had. Maybe I can take some more questions. You guys have been really good with questions. About the state of New York. They would fit in the state of New York if you were to put them all together. But this study shows us that we couldn't really fit them all together because they wouldn't be as efficient and we wouldn't be able to get those 6 blades. Other stuff?
Also, is it more costly to have them on the water and get on the land?
Oh, absolutely. And I didn't get to include that, but some of the people I'm working with are here at the University of Pennsylvania. And that's what they're actually studying, is how do they install them in the ocean, because the farther out you go, you might be able to get higher quality wind, but then what happens with the structures and that happening. So it's not just studying the blades, but that post that supports the turbine. There's a lot of work being done there too, the composites, so that they can be maintained. Just the installation of them is more costly, just like in a oil rig, right?
Is that why there tend to be more on the land compared to
Right now, yes, but also it also depends on how high you can go. Now people are more willing to have them out in the oceans, right? So we might see more of that happening. In England, what's happening is they're installing them. There's so much coast there, and their land is much less available than ours, and they're installing a lot of them. And in Copenhagen, you saw that picture at the beginning. And what's happening though is that the power production doesn't necessarily match their demand, and because of the government subsidies, they're actually paying these wind farmers and the people to produce energy that's not being used. So that's why their research area is trying to figure out what to do with the energy that they're collecting when they don't need it. Okay. Other questions?
Are you familiar with the wind turbines in Atlantic City? They're kind of out in the marshes.
No, I haven't actually seen those. But if you looked, did I have a picture of where they're being installed. If you look at the map of where there's turbines installed nearby, Massachusetts has more than a handful, and you see some in the down by New Jersey, Delaware, right? That area there. None in, very few are being installed, if at all, in Connecticut. I think the Connecticut has good investment in the companies. So the Wind Expo that just took place this summer in Atlanta, and it will take place in Chicago next year, there were 12 Connecticut companies there, presenting their work. So it was either services or manufacturing or production, design of wind-related components. Other stuff?
Efficiency. I mean, wind is free.
Yeah.
So is there any incentive for these to be efficient? Because it seems if you're getting noise, you're probably also getting a lot of thermal waste.
Yeah. Well, they're expensive to install, so you definitely want to get the most out of them, right? And then that noise comes with the fact that it's vibrating. And I think that a lot of that vibration is what's making the nacelle not last as long. So the components and the maintenance of it is just not being kept together. The theoretical maximum efficiency of them was calculated back in 1959, and I think the efficiency of them is somewhere around 62%. And right now they're running at about 40% if installed and new. But when they're installed too close together, where they're getting the turbulence of the previous one, the efficiency drops down to like 20. So if you have GE installing them for you, you really want to make sure you're going to get the most out of them. Good question.
Based on the current rate of technology growth in this field, is there any estimate on when it might be profitable without subsidy?
Yeah, no, you're hitting areas that I haven't researched. Those are really good questions. Especially, I know there's a good part of the audience from the business school, so nice component in there. Yeah. If you find out, come let me know. I'm interested. Okay. And next week in downtown New Haven, there's going to be a talk about renewable energy. It's a forum on renewable energy. I'll make sure to ask that question. That's a good one. Okay. Other stuff?
So is there any potential to doing this in a distributed fashion, like the attractiveness of solar energy is you can slap something on the roof of your house
Yep.
and get something very localized, as
Yep.
opposed to having a central generation system and a distribution system.
Mm-hmm.
And this seems harder to do it for wind.
Absolutely. That's the driving force behind the vertical ones. Because the vertical ones could actually be installed just in you could get one of these and install it, and it might be just the power supply that you need, right? The good thing for this is that for regular blades or regular turbines is that the land underneath them is still usable, right? So yeah, I talk about what I saw in Puerto Rico, but Monsanto can still have all their seeds planted and nothing has changed, right? And wind farmers out in South Dakota are doing just that. They're using the land for multi-purpose. But yeah, absolutely, it's very different than installing it on the roof. And of course, you have to have wind blowing sufficiently. Down here, the wind doesn't blow anywhere to what we would need. But we see the one on the Q Bridge. Right, so.
Addressing the business school question, I've been talking to someone in Wesley and had something related. And the question was, will there be a time, just speculating, when, for example, we located the aluminum industry to Niagara,
Yep.
cheap electricity. So will people start locating high electricity industries to North Dakota?
There's a good political plan there, right? I mean, if you strategize and you give incentives that way, it would make sense, right? Because especially if we have so many problems with transmission and delivery, it would make sense that you sort of bring the industry where you can get the energy. Yeah, but I guess that's driven by anything, right? Solar as well, right? So. Other stuff? I know of, guys, some people have class at 3, so.
Dr. Carnasciali, thank you very much. It was very, very
Thank you. So I used to teach Intro to Sustainability Studies, the EAS 300 class, which satisfies a core curriculum for the university. We tend to have a lot of non-engineers in that class, so if this is a topic that interests you, I'm not actually teaching the class this coming spring or next fall, but it's a class that touches on these topics and others. So that might be a class you want to look into. And if you're an engineer and you want to do undergrad research, come see me. I believe in undergrad research. Thanks.